Now children, third point. If two circles intersect at 2 points, then prove that their centers lie on the perpendicular bisector of the common chord. See, this is one circle and this is one circle. These two are intersecting at P and Q, and PQ is the common chord for both the circles. Then they are saying that the centers, this is a circle with center A, this is the circle with center B. A and B, they lie on the bisector, perpendicular bisector of the common chord. Perpendicular bisector of the common chord they are asking to prove. That means what? This and this, these two are perpendicular, you have to prove, and these two chords are equal in measure, that we need to prove. So what is given to us? We have got two circles with centers A and B, and the circles intersect at P and Q. Now what is RTP? RTP is, you have to prove that AB is the perpendicular bisector of PQ. If you could prove that AB is the perpendicular bisector of PQ, definitely A and B points lie on the perpendicular bisector of PQ. So, when we go to the proof, we have already done one theorem, children, where if there is a circle and a chord is drawn, then the line drawn from the center to the chord is always perpendicular and it bisects the chord. This is what the theorem. Now, in order to prove this, let us suppose that M is the midpoint of PQ. Let M is the midpoint of PQ. If M is the midpoint of PQ, we have to join AP and AQ. Join AP and AQ. So when we are joining this, we are getting triangles. In triangle APM and triangle AQM, in these two, PM is equal to QM. This is what we are considering it. M is the midpoint because we are considering M is the midpoint. Therefore, PM is equal to QM and AP is equal to AQ because they are radii. So, they are equal. AM is equal to AM common. What we did, we are considering M as the midpoint. So these two I am making them as equal. M is the midpoint of PQ. Then when you join AP and AQ, you are getting two triangles. One is triangle APM and another one is triangle AQM. In these two triangles, AP is equal to AQ because they are the radii of the same circle, and AM is equal to AM common. We consider PM is equal to QM. Therefore, these two triangles, triangle APM is congruent to triangle AQM basing on side property. When these two triangles are congruent, therefore, angle AMP will be equal to angle AMQ. Angle AMP will be equal to angle AMP will be equal to angle AMQ. So what we can say? I'll write it here, children. But what we can say, AMP, angle AMP plus angle AMQ is equal to 180 degrees. Why? They are linear pair. So angle AMP plus angle AMP is equal to 180 degrees. 2 times of angle AMP is equal to 180 degrees. Therefore, angle AMP is equal to 180 by 2, that is 90 degrees. This is 90 degrees. Therefore, when you can say that angle AMP is 90 degrees, what we can say? Therefore, AM is perpendicular to PQ. AM is perpendicular to PQ. That means what, children? M is the midpoint and here you are getting perpendicular. That means AB. AB is extension of AM. Therefore, AB lies on the perpendicular bisector of PQ. Therefore, AB lies on the perpendicular bisector of PQ. Perpendicular bisector of PQ. That we can prove, children, in this way. Please write down. Now, fourth question, children. If two intersecting chords of a circle make equal angles with the diameter passing through their point of intersection, prove that the chords are equal. Two intersecting chords. See, AB is one chord and CD is one chord. These two are intersecting, say, at a point. Let me call this point as E. At E, they are intersecting. And they are making, if two chords intersecting, two intersecting chords of a circle make equal angles with the diameter passing through their point of contact. These two are intersecting at E and PQ is a diameter passing through E. Now they are making equal angles. These two chords are making equal angles with the diameter passing through their point of contact. That means this angle and this angle are equal. AEQ is equal to DEQ. This is given to us. Now we need to prove that AB, the two chords are equal. So what is given to us? We have got a circle with center O. AB and CD are two chords. AB intersects CD at E and diameter PQ passes through E. And also they said they make equal angles. Angle AEQ is equal to angle DEQ. This is given to us. These are the two chords which are intersecting at a point E and a diameter is passing through this point E, and these two chords are making equal angles with the diameter passing through their point of contact. That means AEQ is equal to DEQ. Now what is RTP? We need to prove that AB is equal to CD. This we have to prove. Here you have a construction. What is the construction? You have to draw OL, draw OL perpendicular to EA. Perpendicular to EA you can write, or perpendicular to AB also you can write. Similarly, from OM, draw OM perpendicular to CD. This is your construction. Now proof. See children, we have got two triangles at the center. One is a triangle EOL and another one is triangle EOM. In triangle EOL and triangle EOM, in these two triangles, angle L is equal to angle M. They are 90 degrees. And angle LEO is equal to angle MEO. This is given to us. Why is it? When you say that angle AEQ is equal to angle DEQ, then this angles also will be equal. Angle LEO is equal to angle MEO. It is given to us. And EO is equal to EO, common. Therefore, triangle EOL is congruent to triangle EOM basing on angle side property. We can say two triangles are congruent. When they are congruent, what can I say? OL is equal to OM. OL is equal to OM, I can say. That means what? What are we understanding with this? When we say the perpendicular are equal, we can say that therefore AB and CD are at equidistant from the center of the circle. They are at equidistant from the center of the circle because it is circle center. So from here this distance and this distance is equal. We have already learnt that two curves which are at equidistance from the center of a circle are equal in nature. That is what a theorem we have learned. Therefore we can say that AB is equal to CD. Hence proved. This is how we can prove. Please note it down, children. Now fifth sum, children. In the adjacent figure, AB is the chord of a circle with center O. See, this is a circle with center O. AB is the chord of this circle. CD is the diameter. So through diameter D, it is through center O, it is passing through. So CD is the diameter perpendicular to AB. You have to prove that AD is equal to BD. So what is given? You have got a circle with center O. AB is a chord. CD is diameter. And they have also given CD is perpendicular to AB. This much they have given. Now what is RTP? We need to prove that AD is equal to BD. AD is equal to BD. We need to prove. Now let us go to the proof. CD is perpendicular to AB. That means what this implies? Diameter is perpendicular to chord. If diameter is perpendicular to chord, we have already done. If a radius is perpendicular to chord, it bisects the chord. Diameter is perpendicular to chord means, therefore, CD bisects AB, basing on the theorem which we have learned. Let me call this point as M. Okay? Let CD intersects AB at M. This implies AM is equal to BM, because why? CD bisects. CD is bisecting it. AM is equal to BM. Now let us go to the triangles. In triangle AMB and triangle BMD, in these two triangles, AM is equal to BM, we have just now proved, and angle AMD is equal to angle BMD. It is given to us 90 degrees. It is given to us. DM is equal to DM common. Therefore, triangle AMB is congruent to triangle BMD, basing on right angle or side angle side, we will say, because we are talking about this side angle side. Even though it is a right angle, we can't go for RHS because this is hypotenuse, we didn't prove that it is equal. So side angle side property, these two are congruent. When they are congruent, each and every side is congruent, therefore we will say that AD is equal to BD, hence proved. This is the proof, children. Not done. Now the theorem says that angle subtended by an arc at the center of the circle is double the angle subtended by it at any point of a circle. So this is a circle, this is the center. Let us consider PQ as an arc. This arc is subtending an angle at the center, is this. This is the angle subtended by the arc at the center. This is 2 times of this angle that is subtended by the arc. The same arc is subtending another arc on the other part of the circle. So, angle subtended by an arc at the center is 2 times the angle subtended by the same arc on any part of the circle. So, in your textbook, this is given by 3 figures to indicate the different arcs. This is a minor arc. This problem is dealing with minor arc. This is semicircle, and this is major arc. From here to here, this is P, this is Q. So PQ is a major arc. So minor arc, semicircle, major arc. But for all, the namings, the letters are same. They are mentioned with the same because the proof is also going to be same. So what is given to us? We have got a circle with center O, and PQ is an arc. PQ subtends angle POQ at the center, angle and angle P or Q on the other part of the circle. Now, what is RTP, children, here? RTP is, you have to prove that angle made at the center, that is angle POQ, is equal to, it is double to that of the angle made by the arc at the on the other part of the circle, that is 2 times of angle PRQ. This is double to angle the subtended at the two part on the other part of the circle, and there is a construction. What is this construction? You have to join RO and extend it, or draw RS through O. Draw RS ray. So this is yes, this is also yes, and this is also yes. So draw RS ray through O. Draw RS through O. So because of this RS, you are getting this angle as 1 and 2. Name them as angle 1 and angle 2. So this part, consider it as X, and this part, consider it as Y. Now we are getting two triangles, children. Let us go for the proof. Because of this RS through O, we are getting two triangles POR and QOR. In triangle POR, okay, let me take triangle POR. In triangle POR, OP is equal to OR. OP is equal to OR. Why they are equal? They are the radii from here to one part, here to one part. They are radii. So they are equal. Therefore, we can say that angle ORP is equal to angle ORP is equal to angle OPR. Angle OPR, that is equal to X. So if that is X, this is also X. So angle 1 is an exterior angle to this triangle. This is the triangle. See, children, POR is the triangle, and angle 1 is an exterior angle to this triangle. So therefore, exterior angle 1 is equal to angle X plus angle X plus X, that is equal to 2X. So angle 1 is equal to 2X. So similarly, we can prove that exterior angle 2 is equal to 2y. When we talk about this triangle, angle QOR, definitely these two are radii, so they are equal. So this angle will be equal to this angle, that is y. So angle 2 is equal to y plus y, 2y. So the same proof we will get, so I wrote similarly. And we know that therefore angle 1 plus angle 2. Angle POQ is nothing but angle 1 plus angle 2 is equal to 2 times of x plus 2 times of y. That is 2 times of x plus y. Angle 1 plus angle 2 is nothing but angle POQ. Therefore, angle POQ is equal to 2 times of angle, see, angle x plus angle y is angle PRQ. Angle PRQ. Hence, proved. This is the proof of the theorem. Very, very important proof, children. See, I have drawn the other two figures also, but I have not written anything about it because this proof is same for all. For all the things, proof is same. Only figures you need to draw, and you mention that this is the angle subtended by minor arc, this is angle subtended by semicircle, this is angle subtended by major arc. Three figures you draw, but the proof is same for all. Please note it down. I hope I am clear.